Hello, everyone. I'm Enayat Moallemi from Capability Systems Center here at University of New South Wales, Canberra. What I would like to present for today is a bit more focus in one of the components of the modeling toolbox that Sondus just explained, a group of emerging approaches called exploratory modeling for the treatment of many uncertainties which surround the real-world system, and sometimes most of the time challenge the credibility of the result of the system modeling. I start with a brief introductions to the exploratory modeling, then I explain two of the popular approaches from this literature, both in theory and in practice, and then we will finish with some concluding remarks. I think we should start from here that the modeling of real-world system is challenged by the fact that these systems are complex, involving many interacting components, and also by the fact that these systems unfold in a deeply uncertain future. A situation that we don't know anything about the future trajectories, and sometimes we cannot agree on anything because of the diversity of stakeholders that we have and multiplicity of views on the same topic. The classical or traditional system modeling techniques that we have, such as system dynamics or agent-based models, they have proved to be fairly good in capturing at least some aspects of complexity. But they cannot be really reliable on their own for dealing with all forms of uncertainties. They usually reduce the concept of uncertainty to some limited number of future scenarios, and then they project the model behavior within these scenarios. But this approach can cause that we exclude some less likely, but still possible and sometimes very important futures from our scenario assumptions. And this can cause that we end up with some results, with some decisions which would not remain valid under all future conditions. To cover this gap, exploratory modeling was introduced at RAND Corporation in 1993. The core idea of exploratory modeling is that in a modeling work, we cannot rely on a assumedly superior modeling technique or an ultimate model structure or a perfectly fit set of input data or parameters. We instead need to build confidence in our final results by exploring various possibilities under many assumptions regarding the modeling approach that we have, regarding different model structures that we can create, and also different sets of input parameters. Several approaches have been introduced so far based on this core idea, and since the introduction of exploratory modeling, and they've been applied in a variety of applications domains, from water, energy, environment, and climate change to defense and infrastructure. For today's presentation, I would like to give you an overview of two of the recent practices that we have been working in Capability Systems Center from this literature, just to demonstrate how these approaches can deal with the concept of uncertainty and what kind of insights they can generate. I also use an application to show the implementation of these approaches. The application is an acquisition and maintenance management of aircraft fleet. Basically, it's based on the model that Sondus explained. We are interested to know the appropriate size of new acquisition and also the efficient capacity of maintenance in order to secure a certain level of performance in terms of availability of aircraft and also total cost. The first and perhaps the most popular approach within this literature is robust decision making. The focus of this approach is to not only search among most promising futures, but also to search through extreme conditions, unlikely circumstances in the future to identify the vulnerabilities of our strategies. RDM then guides decision makers, modeler, to design some anticipatory and protective measures in order to target these vulnerabilities and therefore to enhance the robustness of the decision. It has 4 steps. It starts with participatory scoping, defining the list of uncertainty, a limited set of initial strategies that we would like to investigate in the future. and our definition of performance. For the list of uncertainties that we have, we run tens of thousands of computational experiments, and each experiment corresponds to one single scenario which can happen in the future. RDM then use a machine learning technique called scenario discovery to find out the vulnerabilities of strategies. In other words, it tries to find out what area of input uncertainty is responsible for the model to behave in a particular way. And by behaving in a particular way, we mean not meeting the performance threshold. Therefore, it would be a vulnerability. Once we identify these failures, these vulnerabilities, RDM guides us how to design protective measures to address these failures and to enhance the robustness. So how this approach is applied in a real case, based on the illustrative example that I mentioned, we ask this question of how vulnerable our predefined set of strategies are in securing two performance thresholds. One is the average flying hour over than a certain limit, and another is total cost lower than a certain limit. We have three sets of strategies which are different from each other based on the size of acquisition and size of maintenance. We have a list of uncertainties which helps us to create different futures, different experiments. We run computational experiment based on the simulation model that Sondus introduced as an engine. And we go through all four steps of the robust decision making one by one. I skip the implementation of steps and just show you the final results and the type of insight that we can get from these results. We can have basically two types of insights from an application of robust decision making. The first is to compare the performance of different strategies statistically. For example, from this box plot, we can see that two of our strategies are more reliable, more robust in fulfilling both objective thresholds compared to another strategy. We can also identify in what percentage of experiment these strategies can fulfill each objective separately. And this information can help decision maker to decide more confidently and to choose among a group of strategies based on some realistic evidence about the future. The second type of insight that we can get is the list of vulnerabilities of the strategies in meeting the performance threshold. And as I mentioned, it's an application of a scenario discovery technique within this robust decision making. As an example, we can see that a medium acquisition and medium maintenance strategy can fulfill the performance threshold related to average flying hour if the time between operational maintenance, which was an uncertainty factor in our experiment, doesn't fall within the specified range of 50 to 140 hours. This information enables decision maker to enhance the robustness of these specific strategies by rescheduling the maintenance line and by adjusting the time according to these failure periods. The second approach is multi-objective, actually a modified algorithm for multi-objective robust optimization. The core argument is that we have some decision-making and modeling problems that we don't want, or we don't want ask decision maker to set a set of predefined strategies initially. We instead want to search through all possible solution space and to choose among those strategies which can fulfill multiple contradicting objectives at the same time, robustly over time. We also want to know when we need to switch, when we need to adopt our strategies over time in order to maintain the fulfillment of these objectives in response to the changing circumstances of the environment. Again, the first step is problem formulation. We define uncertainties, our definition of performance, and the decision variables which shape the solution space. Then we run computational experiments. We map future scenarios. We also cluster these future scenarios with a multi-clustering technique in order to make this large number of experiments more manageable during the modeling process. Then we identified Pareto optimal solutions which can fulfill multiple objectives within each cluster separately. And at the end, we identify the time, the adaptation tipping point when we need to switch between strategies in order to react to the changing circumstance. To show you the type of insight that we can get from this application, again, I use the same illustrative example, but with a new question. So the question is what strategies we need to choose and when we need to adapt our strategies in order to maximize one performance metric and minimize another performance metric over time. And as you can notice, this time we are asking a question of what strategies, because we don't have any predefined set of strategies initially, and this is what we need to recommend to decision maker. We have a solution space of 343 strategies, and these strategies are different from each other based on the size of newly purchased aircraft and also the size of maintenance capacity. We have a list of uncertainty, and we have performance measures with an objective and threshold for each performance measure. We run our computational experiment using the simulation model that we have. We plot the future scenarios, the cluster of future scenarios with respect to the system performance in terms of the availability of aircraft and also the total cost. The scatter plot of this scenario cluster can help decision maker to know what kind of behavior they can expect, in what ranges from the system, what kind of performance they can expect. We also identified the conditions leading to these scenarios, leading to this cluster. In other words, we are interested to know which subset of input uncertainty space is responsible for creation of scenarios within each cluster. And we need to identify these subsets because we want to find out the Pareto optimal strategies within each cluster separately. Once we identify this subset, we use a multi-objective evolutionary algorithm such as Borg or NCGA epsilon 2, which are all implemented in Python, to generate our strategies. And as you can see, parallel coordinate plot is a usual way to represent the generated strategies, as it can shows us the state of different decision variable at the same time with the fulfillment of multiple objectives, that it enables decision maker to make a trade-off between them. We can filter these generated strategies to make them more manageable, interpretable, and to help decision maker to select among them easier. For example, we can choose an uncertainty factor such as required flying hour as a measure to monitor the real changes of environment and to signal for the adaptation of the strategies based on these changes. We filter the generated strategies based on different values of required flying hours, and this can help us to know when we need to switch from strategies of one cluster to another as the observed value of this uncertainty factor changes over time. And it's kind of a roadmap, adaptation pathways for type of strategies that we can have over time in order to maintain the fulfillment of our objectives under uncertainty conditions. We can also filter the generated strategies more strictly. For example, we can filter them for the condition of low required flying hour, and for maintaining the availability of aircraft higher than a certain limit and having a total cost lower than a certain limit. It shows us like more accurate form of strategies that decision maker can choose based on a fulfillment that it makes between multiple objectives. By introducing these two approaches and also the applications that I explained, we got a sense of the type of insight that they can generate and also the type of benefits that exploratory modeling can have for system modeling. To conclude, I would like to summarize some of these benefits again. The first is that exploratory modeling is useful because it can help us to incorporate a stakeholder during the modeling process. It can include the diversity of views by considering a wider space of uncertainty. It also provokes deliberation, experimentation, and learning by the interaction that it creates between a stakeholder on the one side and the result of simulations and the search process in both uncertainty space and solution space on the other side. The second is that exploratory modeling can help system modeling to build confidence in the final results, to gain more robust results, more robust decision insights, and it happens by considering the diversity of future possibilities, not only the most likely possibilities, but also the least likely possibilities. And finally, when we use system modeling for decision making, which is a popular use for system modeling, uh, exploratory modeling can help decision maker to face less failure by providing some protective anticipatory measures to target vulnerabilities in advance instead of facing them and addressing them with reactive and mitigating actions. Considering these benefits, it leads us to think a bit more about the different ways that we can use exploratory modeling for different purpose of system modeling, not only for decision making that I explained here, but also for example, let's say design of a new system or modeling for theory development and for assessing an assumption. It also leads us to think more about the integration of various exploratory modeling approaches that we have together, and also for integrating exploratory modeling approaches with other system modeling approaches, such as many sensitivity analysis and uncertainty analysis, which have been available in literature for a while. And these are basically two main stream of researches that we are following at the moment at the center. That was all for me, and thank you.
Kieran Joyce from Army. Awesome modeling. I'm assuming that you're using some kind of discrete event modeling system as your back end to do all the crunching for you. Mm-hmm. That's it. Are you using a commercial product or something that you've developed yourself? So the second part of the question then is defense. Defense in the early parts of a capability life cycle won't have the ability to do this ourselves, so we'll look to contract that out. But if we're doing this kind of systems analysis for a platform that's going to be in service for 30 years, maybe once we've got our funding and we're in acquisition, we might want to buy that and bring that into defense. If this is a proprietary self-developed kind of software tool, what's the ability to exploit? Can defense buy that? Can our operations research people buy your product and then run it through its life of type?
I think the types of output that this exploratory modeling research provides is more kind of decision support for decision making. I'm not sure if your question was more about how these insights can be used in operation in real practice. Was that the?
Yeah. So both of the models that you've presented have been models that can not just be used in the first year of the capability life cycle to make decisions about what we think we want to buy, but during a 30-year life of type, things will change. The way we train people will change. The prerequisites for the people we recruit will change. Maintenance will change. Artificial intelligence will come in and change our supply chain management. Each one of those changes to a capability system model will mean that we will want to reconsider optimization and save billions of dollars.
Yep.
So do we have to contract you guys for 30 years and keep coming back to you every time we want to change an optimization model? Or can we bring that into defense? Because we have OR people qualified in defense. There's a couple of people up here that are already qualified. We send people through master's courses and we train people on how to use off-the-shelf discrete event modeling systems like Extend, like other products you can just buy. Is there the ability to do that for us? And we can make the savings instead of running a 30-year contract for somebody else to identify savings for us.
Yeah. I think all modeling works, including the model that Sondus explained and also the exploratory platform that I presented, have this capability of being like simplified and presented as a standalone application with a very user-friendly interface. It's more a matter of how we translate these modeling analytical works into like simple interactive menu for the users. And it's more kind of like a design of a system. But I think we need to continuously look into the model structure and change it, because in the time period that you mentioned, our 30 years period, we don't have only change in the state of variable that users can kind of interact and change. We may have also change in the structure of the model. We may have some new interactions. We may have some new uncertainties which we need to include in the model. So I think my answer is both yes and no. In long term, I think we need to revise the model and revise the analytical algorithms to always keep it actually close to what happens in reality. But in short term, of course, it can have like a very simple user-friendly interface for users to interact with.
For this is to be a modeling library rather than a case-specific model. So we would like to make models more accessible, exactly as your need is. Hand you over the library with some training, you can build on your own library. As Enayat says, definitely it's not long-term in terms 30 years. We have to revisit this, update this as the problem and the system changes. But on the short, medium term, definitely that's where we are heading, being able to hand over the power of modeling to the users so they, with some training, a well-educated user can build models themselves. Any more questions? Okay, so I think we'll leave it here. Would you please join me to thank Enayat for the last time?